This presentation is about understanding why the compressions and rarefactions observed during sound propagation in air or in some other gas cannot be due to an adiabatic process. Extending its formula for a speed of transverse waves on a stretched string, Newton initially derived the speed of sound in air as square root of air pressure P divided by the density of air rho. So square root of P by rho. Apart from many physical inconsistencies, this was also an underestimate. That is, this formula gives speed that is lesser than the observed speed of sound. So this was an underestimate and hence wrong. Later, Laplace modified Newton's formula from square root of P by rho to square root of gamma P by rho. He introduced this new factor gamma, where gamma is the ratio of heat capacities. Gamma equals Cp by Cv. And thus, he corrected the underestimation error in Newton's formula. Or so we think. Here we shall see that even this Laplace's formula is conceptually a wrong way of looking at the speed of sound. Even though the formula matches the speed of sound in gases under various conditions. The theory and any of the way used to derive this formula is not at all sound. Since it is based on the assumption of adiabatic processes, let us take a closer look at those adiabatic processes. So consider this gas cylinder piston system. A cylinder is placed vertically on the surface of the earth. The piston weight is balanced by the pressure of the gas particles. We get Pi equals m subscript I into G by A. P subscript I is the pressure of the gas in the initial state. M subscript I is the mass of the piston in the initial state. G is the acceleration due to gravity. And A is the area of the cylinder cross section. Mi into G indicates the weight of the piston. Mi is the mass, so Mig indicates the weight of the piston or the force exerted by the piston on the gas. Force per unit area is pressure, hence Pi equals Mig divided by A. Essentially, the high pressure below the piston is providing the lift to hold the piston up. The piston is practically floating in air. The movement of piston is assumed to be frictionless. There is no exchange of heat energy or the particles with the sides of the cylinder or through the sides of the cylinder or with or through the piston. So in any case, the gas energy is not being, or the particles of the gas are not being exchanged with the surroundings. So basically this is an adiabatic process because there is no exchange of heat energy or exchange of mass with the surroundings. Let there be n particles at the initial temperature Ti and initial pressure Pi. Let the initial volume occupied be V subscript I. We already know that Pi is this. Pi equals Mig by A. We saw that earlier. Note here that Vi equals AZI. So Vi is the volume and A is the cross-sectional area of the cylinder, which is maintained a constant in this setup. And Zi is the initial height of the gas. The height of the gas is variable. The cross-sectional area we keep it as constant, but the height we let it as variable. It varies according to the external conditions. Suppose we replace the mass Mi, that is the mass of the piston, by some other mass Mf. That is, Mi is replaced by Mf. Then at the final state, the pressure Pf, P final, P subscript F means the final pressure, Pf, of the system is related to the final mass Mf as Pf equals Mfg by A. So note, in the initial state before the piston mass was changed, when it was just mi, the pressure was pi equals mig by a. So I, subscript I is initial state, subscript f is the final state. So now the pressure is this. Initially it was pi, now it is pf. Since we have changed the mass on the piston, we have also altered the potential energy of the system. So the initially potential energy of the piston was mi(g)zi. Now the new, when we replace mi by mf, it becomes mf(g)zi. So the change in the potential energy is mf minus mi(g)zi. So this is the externally added energy. This is an external forcing, which basically means we have added this much potential energy into the system. There is no change in heat energy as such, but there is change in mechanical energy or the external work term. So we know pi equals mig by a and pf equals mfg by a. Multiplying the initial and the final pressure terms with their respective volume terms, vi and vf, we get pi vi equals mig(zi). So vi is just a zi. So when we multiply that, the a gets cancelled, zi remains. So pi vi equals mig(zi), pf vf equals mfg(z)f. And from the ideal gas laws, we know pi vi equals nkti, where ti is the initial temperature, pf vf equals nktf, where f is the tf is the final temperature. N, it should have been a capital N. Capital N is the number of particles and k is the Boltzmann constant. So PIV equals NKTI. This is the ideal gas law. So using these two, the second and the third equations, we get NKTI equals PI equals MIGZI. So all these terms are equal. And similarly, in the final state, NKTF equals PFVF equals MFGZF. So all these terms are equal both in the initial and the final state. So the net energy E naught of the system in the initial state is given by E naught equals F by 2 NKTI. Here F, where F by 2 is, F is the degrees of freedom. The subscript F refers to the final state, and this is the alphabet F refers to the degrees of freedom. So F by 2, F is the degrees of freedom of this gas particles, F by 2 NKTI. This is the amount of heat energy that this gas has. And MIGZI is the amount of potential energy that the piston had. This is the gas and the piston system. This is the whole energy. That is the heat energy of the gas plus the potential energy of the piston. So this is like the first law of thermodynamics. This is the total energy conservation term. So this is the total energy of the system. And we can write it as 1 plus F by 2 NKTI, because NKTI and MIGZI are the same. So we can either write 1 plus F by 2 NKTI or 1 plus F by 2 MIGZI. So that will be the total energy in the initial state. So after we change the mass on the piston from MF to MI, we are adding this much potential energy into the system. So this was the total initial energy, 1 plus F by 2 MIGZI. And this is the potential energy change that we have added to the system. So the final energy E is the initial energy plus this potential energy change. So in the final state, if MF is the final mass of the piston and ZF is the final height that the gas reaches, then this total energy must be equal to 1 plus F by 2 MF G ZF. So using this equation, we can find out what ZF, given ZI, MF, MF, MI and all these terms, we can find out what should be the ZF for the given MF. So if we change the mass to MI to MF, the volume or the height of the gas changes, and we can use this equation to find out how the change happens. So this is the actual adiabatic process. So for the correct adiabatic process, the full accurate way in which we can know the volume change is using this equation. ZF equals ZI into M subscript I F by 2. Here again F is the degrees of freedom, and plus M subscript F, where M subscript F is the final mass. So this is the expression, Mi F by 2 plus MF plus divided by 1 plus F by 2 MF. So Zi is the initial height of the gas and ZF is the final height of the gas. Usually we are not used to deriving these expressions. This is probably the first time you would be seeing this. What we are used to seeing is the approximate version of this expression. Basically, we assume that MF is very close to MI. So we assume mf equals mi plus del, where del is much smaller than mi. So del by mi is very, very close to 0. So in that state, we assume mf equals almost mi, which is mi plus some small quantity del. So we replace that in both the numerator and the denominator, and using the first order Taylor series expansions, we get this approximation. So zf is nearly equal to zi into 1 minus f by f plus 2 del by mi. Here note that del is very close to 0, or del by mi is very close to 0. And again, using the approximation, usually we are used to the reverse approximation. So if there is this term 1 plus del by mi to the power of something where del is very small, we do this. We just multiply this exponent term with the whatever the term del by mi here. We are doing the reverse of this. So if del is very small, we can also use this approximation that this is nearly equal to zf is nearly equal to zi into 1 plus del by mi to the power of minus f by f plus 2. So this is the approximate version. This is the accurate version. And we know pf and pi have these forms. So we get that pf equals pi into mf by mi. So this is a simple relationship we get between the pressures and the masses. Masses on the piston. So pf equals pi into mf by mi. So replace mf by del plus mi. We get pf equals pi into 1 plus del by mi. So this term inside the square bracket 1 plus del by mi is the same term that appears in this volume or the height equation, zf equals zi, this term. So using this term, we'll eliminate this 1 plus del by mi using this z equation. So basically we get pf equals pi into zi by zf power gamma, where gamma is nothing but f plus 2 by f, where gamma is the ratio of the specific heats, which is also equal to f plus 2 by f, where f is the degrees of freedom. So basically this, since the area is constant, we can multiply just azf in the top numerator and the denominator. So finally we get this expression, pi vi power gamma is nearly equal to pf vf power gamma. So the initial state pi vi power gamma expression is nearly equal to the final state pf vf power gamma. Note, this is the usual adiabatic formula that we are used to, but this is a very, very inaccurate or a very highly approximate version. This adiabatic formula is pretty inaccurate, and it works only when the final pressure pf is nearly equal to the initial pressure vi. The perturbation is very, very minute, really tiny perturbation. It works. We can use this formula. This is the approximate version, but for accurate version we can always use this. Here there is no boundation that pf should be nearly equal to pi. Mi and mf can have any relationship, can be very small, very large, or whatever. So this is the accurate version, and this is the approximate version. One thing to be noted about this is these kind of adiabatic process that we saw here is technically irreversible. This is not usually mentioned, or it is not even known, but this process is technically irreversible because there will be a leftover potential energy effect. So for example, on the extreme left, we assume that this is the initial state. The temperature was Ti, the pressure was Pi, and the mass was Mi. So we replace this mass Mi by some final mass Mf. So that is essentially we are adding this much potential energy into the system, Mf minus Mi into Gzi. So basically we are adding that energy at Zi. So initially it was Mi Gzi, finally is Mf Gzi. So the difference is Mf minus Mi Gzi. So similarly in this final state, in the middle one, what we do is we will replace this Mf back by Mi. So in the first step, what we did is we replaced Mi by Mf. In this step, we'll replace Mi back. We'll replace this Mf back by Mi. So it's like a full circle. We started with Mi, we changed it to Mf, and we get back to Mi. So what happens to the state of the gas? Basically at this step, what we did is we added this much energy, Mi minus Mf Gzf. So this is happening at id Zf, and this is the old mass Mf, and this is the new mass Mi minus Mf. So note that the summation of these two potential energies, these are not equal and opposite. If we add them, there will be a definite residual effect left over. It will not be zero. This mf minus mi gzi plus mi minus mf, this is the net potential energy added in these two steps. If we add up, it is not zero. Therefore, what happens is when with mi, no doubt the final pressure of the system will be the same as this in the first step, pi, because the mass is mi. But what happens this, there will be this residual potential energy left over, which appears as higher temperature. This temperature, the final temperature that we reach will be higher than the initial temperature Ti, and the final volume, whatever we reach, will be higher than the initial volume Zi. So it's not exactly reversible. So even if we put Mi back at this stage, we will not get back Ti and Zi as its temperature and height values. There will be some leftover, so that appears as the enhanced temperature and the enhanced volume. So this makes it irreversible. So no matter what we do, if we replace Mi by Mf and we get back to Mi, there will be an excess potential energy added into the system, shown by these two terms on the top, and that appears this residual effect, or like probably kind of a hysteresis effect, is left over in the gas column. So basically, when we add these two potential energies terms in the first two steps, we'll get a term involving mf minus mi whole square. So no matter what mf minus mi is positive or negative or whatever, this residual term will be positive. So there will always be this excess potential energy residue left over in the system when we do this in a cyclical manner. More importantly, what we need is when this adiabatic process happens, that is when we impose this external pressure, some Pf, the final external pressure Pf, we expect that the Pf remains constant. That is basically in an adiabatic process, the enforced external pressure, the final state pressure, has to remain constant till the system, this gas Pi, this gas pressure Pi, till that system equilibrates with the imposed external pressure. Since till the time it gets equilibrated with the outside pressure has to remain constant. So that is when we get this formula Zf equals Zi into whatever this in the square bracket, which in an approximate version becomes Piva power gamma equals constant, or Piva power gamma equals Pfvf power gamma. So for this to work, this Pf has to be constant. So initial state was Pi, which changed it to Pf, and it was constant till till the internal pressure of the gas becomes Pf at equilibrium with the outside pressure. The Pf has to remain constant. Only then we can apply this formula. Otherwise, we can't use this. But basically, if it is a variable pressure, then we cannot use this formula, so that's why we have written non-adiabatic here. No matter what, the internal energy or the heat energy may not be exchanged, the particles may not be exchanged. Technically, it may be an adiabatic process, but if during this compression or the expansion, if the external pressure keeps changing, and there is no equilibration funda, that the internal pressure comes to equilibrium with the final pressure. If that kind of process is not happening, then we cannot use this formula simply. So in that sense, it is a non-adiabatic process. So in any case, the supposed compressions and the rarefactions that we observe in the sound propagation cannot be due to adiabatic process, because say for example, there is this compressed region. So in the next few time steps, it will become rarefied. So till it become rarefied, the outside external pressure, the patches of air around this region have to maintain that rarefied, the low pressure, till this compressed region becomes low pressure. But that is not what is happening. All the regions are having continuously varying pressure. The compression becomes low, and the rarefied regions keep acquiring higher pressure. Actually, for half the cycle, it so happens that the region where the pressure is high keeps increasing its pressure, and the region where the pressure is low keeps reducing its pressure until it reaches the lowest pressure. So in their sinusoidal oscillation. So basically these neighboring regions are not actually enforcing their pressure on each other like we expect in this adiabatic process that we described above. So the outside pressure or on this patch or on this compartment of gas Pi, the outside pressure Pf is not being maintained constant. The Pf or the outside pressure is continuously changing, so hence we cannot really use this adiabatic formula for this these kinds of compressions and rarefactions of sound waves. So we end our presentation on that note. Basically that we cannot use this adiabatic formula PV power gamma equals constant. So in this presentation we saw that both the transverse wave formula based on Newton's derivation and the longitudinal wave plus adiabatic process based Laplace derivation are both the wrong ways of deriving the speed of sound. In fact, the basic physics does not support either of these processes. That is, we can neither use PV equals constant, which implies an isothermal process, or PV power gamma equals constant. We can neither use neither of these formulas, PV equals constant or PV power gamma equals constant, for the compressions and the rarefaction events observed during the propagation of sound in gases or in air. So basically, even though using this PV power gamma, using this idea that PV power gamma is constant gives an expression, because we use this to arrive at the Laplace formula. Even though using this gives the correct expression, which is consistent with the observed speed of sound. Basically, gamma p by rho is consistent with the observed speed of sound, but the derivation is not proper. Derivation is not proper because we cannot physically, it is not allowed to use PV power gamma equals constant expression, because the external pressure is constantly changing. We don't know how the exchange of energy is happening between the piston and the gas particles and so on. So we did not know this. We cannot apply this PV power gamma equals constant in this case. So the final external pressure, so for it to be adiabatic, or for it to be, so that we can use PV power gamma equals constant, for it to be adiabatic, rather for us to be able to use this formula, the final external pressure must remain constant until the gas pressure equilibrates with it. So Pf should remain constant till Pi becomes Pf. There cannot be a variable Pf outside. So that is why we cannot use. So that is why both this is wrong. Not only because the theory is wrong, even the values do not match the expected speed of sound. Yeah, this one matches with the experiment, but still the theory is wrong. We cannot use the formulas that we use to derive this. So basically it is likely that the correction suggested by Newton in a later work, in his second edition of Principia, that might hold the key to derive an expression compatible with the kinetic theory of gases and elastic collisions. So basically what we do, if it has to be consistent with the kinetic theory of gases and elastic collisions, both these above formulas, Newton's first edition of Principia or the Laplace's, they cannot be used. They are not compatible with that kinetic theory of gases. Here, basically we have to derive it based on the elastic collisions. Then it will be properly compatible with the kinetic theory of gases. So here, in whatever v is the speed of sound, and we expect a formula like this from the Newton's later work. V is equal to Vx divided by 1 minus d by L naught. So v is the speed of sound. Vx is like the average or the typical velocity observed along some x-axis. So this axis can be oriented in any arbitrary direction. So we are just naming it Vx. So Vx is some typical velocity along the direction that the particles have along the direction of the wave propagation, and d, this small d, is the size of the particles, and L naught is the average spacing between the particles. So d by L naught is the packing ratio. So the final formula for the speed of light may have some form like this: v equals Vx by 1 minus the packing ratio. Newton's later work gives a basis for this. So this may be the correct formula for the speed of sound. We shall look into it in the next video. So we end that here. Thank you.